So, have you ever stopped and wondered how your brain's messy, creative, and sometimes totally random thoughts can get turned into something a computer can actually understand and use? Well, that's where the magic of propositional logic comes in, and we're about to pull back the curtain on how it all works.
Okay, so here's the core puzzle we're trying to solve, right? Computers think in black and white, zeros and ones, on and off. Our language, though, it's a whole spectrum of nuance and feeling. So how in the world do we bridge that massive gap?
I mean, just look at the difference. On one side, you have the beautiful, complicated mess of human language, and on the other, you have the stark, simple, absolute world of a computer. To get these two to talk to each other, we need a translator. We need a new, ultra-precise language that both can agree on.
And just like any new language, we've got to start with the alphabet. So let's dive in and look at the most fundamental letter, the absolute basic building block. This little guy is called a literal or a variable. The best way to think of it is like a light switch. It can only be on or off, true or false. A statement like, "It is sunny," works perfectly. "The cat is asleep?" Yep, that works too. But something vague like, "It's kinda nice out." Nope, a computer can't do anything with kinda. So let's take two of our light switches, A and B. When you put them together, how many combinations can you get? Well, there are four, right? Both can be off, both can be on. A can be on while B is off, or B can be on while A is off. This simple grid of possibilities is the basis for a really powerful tool called a truth table.
But having a bunch of separate on-off switches isn't super useful by itself. We need a way to connect them, to build bigger, more complex ideas. And the two most basic ways to do that are with the connectors OR and AND.
First up is OR, and you'll see it written with this little V symbol. I like to think of OR as the optimist. As long as at least one of its inputs is true, the whole thing is true. The only way for an A or B statement to be false is if both A and B are false.
And next we have AND. Now, if OR was the optimist, AND is the strict perfectionist. For an AND A statement to be true, both A and B absolutely have to be true. No exceptions. If even one part is false, the whole thing just collapses. It's an all-or-nothing deal.
All right, you might want to brace yourself for this next one. This concept is called implication, and it's where a lot of folks get tripped up at first. But trust me, it's also where this logic starts to get really, really powerful. This is your classic if-then statement.
Let's ground this with a simple, real-world example so it's not so abstract. Imagine we make a promise. If it is raining, then the floor is wet. Got it? Now we're going to test if we kept our promise in every possible scenario.
Okay, let's walk through this together. First row, it's raining and the floor is wet. Did we keep our promise? Yep, so the statement is true. Second row, it's raining but the floor is dry. Uh-oh, we broke our promise. This is the only time an if-then statement is false. Now, for the weird part, look at those last two rows. In both cases, it is not raining. Well, our promise was only about what happens when it rains. Since it's not raining, we haven't broken our promise, have we? It doesn't matter if the floor is wet for some other reason or if it's dry. Our promise is still intact. And that's why the whole statement is still considered logically true in those cases.
All right, let's move on to the biconditional operator. This one is way more intuitive. Think of it as a strict two-way street. It's not just if A, then B. It also means if B, then A. They are completely locked together.
And the perfect example for this is a password. You can log in if and only if you have a valid password. See how that works? The two conditions are inseparable. You can't have one without the other. It goes both ways. And the truth table for this makes total sense. The statement is only true when both sides match. Both are true? Yep, that works. But look, both are false? That's also true. Because if you can't log in and you don't have a valid password, the system is working exactly as it should. It's only when you have a mismatch that the logic fails.
Okay, so we've learned the alphabet and some of the basic grammar. Now for the fun part. Let's actually put on our translator hats and turn some everyday English into the precise language of logic.
Let's start with, it is sunny and it is not raining. We can assign S to sunny and R to raining. The word not gets its own special symbol, that little sideways L, which we call a negation. So the sentence just becomes S and not R. Easy enough?
How about this one? Either it is a weekday or it is the weekend. Well, that word or is our big flashing sign, isn't it? We just assign a variable to each part, and it becomes W1 or W2.
And of course, we have our good old if-then structure. If it is snowing, then the roads are slippery. That sentence structure itself is practically screaming at us to use the implication arrow. So S implies R.
Now, let's try a more complex one. If it is daytime and it is not raining, then it is warm. Don't get intimidated, we just tackle it in pieces. First, the if part, daytime and not raining. We know how to write that, it's just D and not R. Then we handle the then part, it is warm, which is just W. Finally, we connect those two chunks with the implication arrow. And just like that, we've built a complex logical statement, step by step.
And there you have it. We've bridged the gap from our messy, nuanced thoughts to the precise language that computers need to operate. This is the very bedrock of everything from your phone software to advanced AI. Now that you know the rules, I'll leave you with a little challenge. Look at this expression. Under what conditions for A, B, and C would this entire statement be true? Give it a shot. I think you'll find the answer is pretty straightforward now.